Hey, thanks for tuning in. I'm giving a quick talk on BikeBench, a bicycle design benchmark for generative models with objectives and constraints. My name is Lyle Regenbetter. I'm a PhD candidate at MIT, and these are my wonderful co-authors who have made this work possible. Now, I'd like to start off by asking, what do you think is AI's final frontier? Now, since AI has already transformed the digital world, one might reason that embodied intelligence might be the final frontier, things like robots and autonomous vehicles. But what about designing a robot or a car or a plane? That's probably much harder, right? Now, I don't know about you, but personally, I'd feel much safer in an AI-piloted plane than an AI-designed one. So therefore, I'd posit that engineering design might be AI's final frontier. Once AI can design the robots and the machines to build the robots, that's when AI will truly be omnipotent. Now, unfortunately, AI is pretty awful at design, and this is for a few reasons. First, our amazing VLMs aren't so good at design. So if I want to actually manufacture a design, a generated image or a text description of a design won't really cut it. Instead, I might need exact parametric data, for example. And second, Gen AI models are trained in similarity, but in design, we care about design quality and constraint satisfaction and maybe even diversity rather than similarity to a data set. And of course, we need benchmarks. That's what this talk is about. We're introducing BikeBench, a Gen AI benchmark for bicycle design, which is based on a data set of 3,800 parametric bicycle designs, each represented using 64 mixed modality parameters. And BikeBench evaluates statistical similarity, design quality, constraint satisfaction, and design diversity. So naturally, you might wonder how we evaluate things like design quality or constraint satisfaction for bikes. And BikeBench actually evaluates 40 distinct constraints and 10 unique objectives. Now, some of these are closed form, while others are data-driven, evaluated using surrogate models trained on 5 data sets with thousands to millions of designs. And we have checks for geometric validity, evaluating part collisions or violations of physical laws. We also consider structural soundness under several loading conditions. We look at bicycle aesthetics, evaluating how faithfully a design matches a given text prompt or reference image. And this functionality is actually supported by a massive data set of 1.6 million procedurally generated bikes, as well as their corresponding rendered images. BikeBench also features a data set of 10,000 real human evaluations of bikes, allowing BikeBench to estimate human subjective preference for bikes. And finally, we also evaluate aerodynamics and ergonomics, which are both functions of the rider's dimensions as well as the bike design. So collectively, these requirements for bicycle designs constitute a huge multidisciplinary and multimodal design evaluation suite. And the benchmarking procedure looks like this. So given a rider's geometry, a reference text prompt, a target use case, and a data set of existing designs, models try to generate high-performing designs that satisfy these conditions. And they can evaluate 1 million bikes in their search for good solutions, and then ultimately they're asked to generate 100 designs for each of 100 unique conditions. And then BikeBench evaluates these designs using the objectives and constraints and metrics that we discussed. And this paradigm can actually be used to evaluate all sorts of models. So in our paper, we evaluate 4 classes of approaches: large language models. We have a whole querying procedure, which you can check out in the paper. Design optimization, which searches the design space by iteratively querying evaluators, but doesn't use any sort of data-driven learning. There's a class of models that we call generative optimization algorithms, which query the evaluators during training to steer their learned distributions towards higher performing and constraint satisfying regions of the design space. And finally, tabular generative models, which are intended purely for distribution matching on mixed variable tabular data, but are agnostic to design requirements. And here I've picked the best method that we tested from each class and ranked ordered the results under a few key metrics. So in general, LLMs struggle across the board, while generative optimization excels in design quality and distributional similarity. Now, of course, these models have different specialties, and some of our benchmarking choices will unavoidably tend to favor certain classes of methods. So for this reason, the benchmark can actually be configured to compare models under different evaluation budgets, or one-shot generation, conditional or unconditional evaluation, or mass constraints, and much more. But under the standard settings, these here are the results. So lastly, we encourage you to benchmark your methods, Gen AI models, LLMs, optimization algorithms, and everything in between. Try it out. We have features to generate these nice scorecards, and we have a leaderboard where you can submit your results and filter the best models under different benchmarking settings. So we're really curious what you come up with. Let's figure out how to make machines design machines. Thanks for the interest, and happy benchmarking.